Today's lesson will be about groundwater. Groundwater is water that enters the ground and fills open spaces in soil and sediment, as well as openings in bedrock, including cracks and spaces. Usually, groundwater is fresh water, and it's generally free of organic pollution, germs, and dangerous contaminants. If we want to look at the distribution of Earth's water, let's first look at this green section here, okay? 97% of Earth's water is salt water that we find in our oceans, and 3% of that is fresh water. Now, if we take that 3% and we break that down in this brown section, we'll see that of the fresh water, about 68.7% is in our ice caps and our glaciers, 30.1% is found in our groundwater, and less than a percent, 0.9%, is found in other locations. Now, of that 0.9%, we're going to find it in lakes, swamps, and rivers. So you can see that most of that other percent here is in lakes, 11% in swamps, and 2% in rivers. So of our fresh water, which is a significantly small piece of the amount of water we have on Earth, most of it's ice caps. But today we're just going to talk about this 30% of this 3%, which is our groundwater. To really understand our groundwater, we first have to have a basic understanding of the water cycle. We talked about this yesterday in our activity, but just as a review, here it is. Precipitation is water that's going to fall down to the earth. Infiltration, which we're going to talk a lot about today, is when water seeps into the ground, and that's obviously going to be our groundwater. We could also have runoff, where water is going to, instead of seeping in, just flow down the surface of the earth. Over here, we can have evaporation, where liquid water is going to turn into water vapor in the gas form. We can have transpiration, which is water kind of evaporating off of plants. So I always think of T stands for trees, where we're coming off of the plants. And then condensation is when we have that water vapor turning back into water droplets in the clouds. Okay, so obviously this is a cycle. It's going to continue. And if you need more help with that, then you need to review that activity we did yesterday. So specifically, we're going to talk about infiltration. Like we said in the water cycle in the last slide there, it's the process of water soaking into the ground. So I always think infiltration is going into the ground. That's obviously under the influence of gravity. So in this chart here, you want to fill this in. You probably want to pause the video to do so. But infiltration is when obviously sinks into the ground. Runoff is when it's going to flow off the surface. So we want to figure out what are the things that are going to make water enter the ground versus not enter the ground. So first word here is whether it's saturated or unsaturated. If the water is already saturated, meaning it's already filled with water, you're going to have runoff because no more water can fit in. If you've ever tried to water a plant and you overwater it and you see that puddle of water on the top, that's runoff, okay, because it can't infiltrate. So ground has to be unsaturated. Obviously, it has to have space for water to go into. If the ground is frozen or not. If the ground is not frozen, obviously water can seep in, but if it is frozen, it's going to be impermeable. Water will not be able to infiltrate. Precipitation has to be rain. Snow, is just going to pile up at the top, so that's not going to have infiltration. Slow, gentle rain versus a rapid, intense rain. If you've ever seen a very heavy rainfall, water can't seep in that fast. So what's going to happen is eventually it will seep in, maybe, if there's enough space. But at that moment, if it's too intense, runoff will occur. It has to be slow enough for the ground to accept it. Vegetation is going to help infiltration. Areas with no vegetation are going to produce more runoff. And then obviously gentle slope versus steep slope. If you have a steeper slope, that's going to cause that water to not have time to seep in. It's just going to run right off the surface. Okay, so when we look at this diagram, after water has infiltration or seeped into the ground, what is going on underneath there? So this is a cross-sectional diagram of the crust or the top layers of the earth here. Few words you need to know. Zone of aeration. This is right here at the top. This is the region which is mostly filled with air, and I always think aeration is air. Zone of saturation, this is the area of, think what the word saturated mean, filling with water. This is the space in the rock that is filled with water. So aeration is just the space in the rock filled with air. Saturation is the space of the rock filled with water. And then the water table is the upper limit of the zone of saturation. So you can see here the water table is where pretty much all this groundwater is stored. The height of the water table is going to depend upon how much water is actually seeping in or infiltrating, the horizontal flow of groundwater, and also the usage. So you can see here at A and B, there's some wells that are dug in here if you have a well at your house. Your well goes down to the water table. If it didn't, you wouldn't be able to get any water at your house. So if you over pump a well, your well will go dry, and that's because you've used all the groundwater, and that would be your usage here. You're not just going to get any more water. So your well has to be dug down to the water table. How does climate affect your water table? Well, humid climates are obviously going to be climates that have more water in the area, and typically your stream is going to be the height of your water table. So groundwater will feed that stream here. In an arid climate, that's when you're going to see like streams even dry up. They're going to lose their water table is really low. So your climate really affects how much groundwater you're going to have. Now, factors affecting the movement of groundwater, which is how much water that rocks can hold, truly depends on these two terms, which we're going to talk a lot about today, which is porosity and permeability, okay? Permeability is the rate at which liquids pass through pore spaces. Porosity is the percent of pore space. So we're going to go through this here, a couple of slides, really make sure you know the difference here between porosity and permeability. Okay, we're going to start with permeability. Permeability is the rate at which water will flow through rock, okay? If you have a larger size particle, like a sand, a gravel, a pebble, okay, they're going to allow water to move through them faster than smaller particles, because smaller particles, the closer they get, the more impermeable that layer is, meaning water can't flow through it. So the larger the particle, the easier it is for water to flow through. So if we take a look here at this picture, I want you to go ahead and take your pencil and trace what I'm doing here. If we had water flowing on this ground, okay, your water would flow almost like a maze through these spaces, okay, all the way through these spaces. So the further, that was kind of hard, right? So the further spaced out these things are, it can go a lot faster, and I can even draw this a lot faster through the rock itself. So the bigger particles you have, the more permeable it is, the easier it is for water to travel through. So in this one, which one is easier? It's going to be answer choice B. Okay, porosity then is how much pore space you have. This depends upon the amount of space in between your grains, okay? We're not talking about water going through now. We're talking about water remaining within these spaces. So in these two pictures, the blue obviously is the water. You can see there's a low porosity up here. There's not a lot of space. Down here, there is a lot of space, so we have a high porosity. So there are some things that are going to affect the porosity. The shape is one thing. If you look at these pictures down here, the rounder the shape of the sediment, the more porosity or the higher porosity you're going to have, because there's more space between your grains. So what I want you to do is to take your pencil and kind of color in all these spaces in each of them so you can actually see the difference between the spaces. So round, you're going to have way more space, flat, less space. Sorting here, remember, sorted is they're all the same size together. Unsorted is all mixed together. What's going to happen here is sorted are going to have more space between their grains, and unsorted are going to have less. If you can see here, these small particles, they take up that pore space. So there's less pore space there in the unsorted pile. Again, color that in to see the difference. Packing's a little bit different too. If you have them all tightly packed together, you're going to decrease your pore space or decrease your porosity. Loose packed particles, there's going to be way more pore space in here. So again, color in all this pore space so you can see that the loose packed has a higher porosity, has more space between the grains, and the tightly packed has less porosity, has less space between the grains. So the one thing that does not affect the porosity is the size. Okay, so again, porosity is a percentage. How much open space do I have within the object? So if we had small, medium, and large, and they were all the same volume, just different size beads or sediments that we had in here, if we poured water in there, you would actually find that they would have the same percentage of pore space, which means they have the same porosity. So let's take a look at the sand. In this animation, you can see this is small, medium, large, and then unsorted, okay? So what I'm going to do is I'm going to release this water. And you can see that in the small, medium, and large, all of the same shape, okay, these are all the same volume, they have the same porosity. This one over here has a lower porosity because it's unsorted. It has all those small pieces mixing in, creating a lower porosity. So when we look here at this next slide, we ask the question, which has a higher porosity? Again, porosity is the amount of pore space. So even look at it. You can color it in if you need to. Here's A, here's B. If you fill in and color, you should see that A has the higher porosity. So what I would like you to do here, we have 4 different rock types, okay? I'd like you to write in, you can do an H or an L. Does this have a high porosity, a low porosity, a high permeability, or low permeability? Okay, so you're going to do that for all 4, and then pause the video right now so then you can check your work. And here are your answers, okay? Again, low porosity, low permeability, no space in between, so the pore space is low. And if there's no pore space, how can water flow through it? So it has a low permeability. Here, there is some spaces, but the way the shape of these, if I poured water on this, it'd be really hard. Remember that maze? It'd be so hard for that to go through, so it'd be a low permeability. Here we have lots of space, which is high porosity, and since we have lots of space, we can have a high permeability here. It'd be very easy to maze through this quartz sandstone. And then here, this is all unsorted, low porosity. There's barely any pore space. I couldn't color any of this in. And there's no place for water to flow through, so it's a low permeability. The very last thing is capillary action, okay, or capillarity. This is the upward movement of water through soil. This can pull water from that water table, as we talked about, all the way up to plant roots. Now, this works the best with small particle sizes. So if you look here, this is the largest tube, this is the smallest tube. You're going to see that in the small tube, water is going to rise the highest. Just like small, tiny tree roots, they're going to be able to pull that water up to the tree itself. Now that obviously defies gravity, so this is why it's a specific thing that we're going to talk to you about. So if we look here, we can see in this picture that in the small tube, you're going to see water go up all the way. In the big tube, nothing really happened, and we're relating that to tree roots. So we have the water from the water table. These tree roots are pulling that water upward, which is that capillarity, to the tree itself. The very last thing we need to discuss is what could be some groundwater problems. Pollution of the aquifers, which are underground reserves of water. Any kind of pollution of your groundwater is a very negative thing, which is going to, when you own a house, that's going to be a big thing for you. Obviously, you want your groundwater protected. Sewage seeping into the ground, sometimes that happens, especially if you have like a septic tank. You know, we could get into that, but we're not going to today. And then saltwater invasion. If you live near the coast, obviously the ocean, sometimes that saltwater, because it's more dense, kind of seeps underneath the fresh water. And if your well's deep enough, sometimes you can get that in your groundwater, which can be a problem. Okay, so groundwater is just water that's underneath the surface. Remember, porosity and permeability are the big things that we talk about when we discuss how water is going to infiltrate and be in that soil.